Then let's go to the second part about the conditional expectation function. First of all, in case some of you does not take the probability or statistic classes, I will first introduce some basic notations. The first one is the mean or expectation of a random variable y. So with discrete support of a random variable y, the mean value of it can be expressed as ey, which means the expectation of it. And it is the summation of the probability of an event occurs and the event itself, and multiple the event itself. So for example, if we have like 90 professors and 30 of them have 10 years of teaching experiences, and 30 of them have 20 years of teaching experiences, and 30 of them have 30 years of teaching experiences. And you can see they all take up 1/3. And for less professors, they have, maybe we can just simply using the 1,000 and 2,000 and 3,000. And then we can compute the average income of these professors, and the probability of the income 1,000 occurs is just 1/3, and also for 2,000 and 3,000. And then we can finally get the average income, that is 2,000. So it's actually the average value of the income, but it uses another notation to interpret it. And I hope you can understand this kind of way of interpreting. And then it comes to the conditional mean or conditional expectation, which is the expectation of y conditioning x. Here x means the condition. It could have more than one condition, and I will eventually show you that one. And for example, it's kind of like the mean value of wage when the professor has 12 years of teaching experiences, or maybe like the average height of female students, kind of those things. You can add anything to be the condition. And then we can write the equation of the conditional expectation function, denoted as CEF. So here, it means a bunch of conditions, like the education, so we want to estimate the income of a person whose education is maybe 12 years, and the gender is female or something like this. So you can add other conditions. And the capital X is a vector of conditioning variables. And then the CEF is a function of x, and understood it as when x takes the value of x, when this x takes the value of this x, and the average value of y is just mx. We will use this equation later for proof, and I hope you can understand it. Although it looks like complicated, but it's not so hard to understand, I think. And since we have mx, so let me write down it here. So this is the mx. And we can estimate the CF error. So CF error E is defined as the difference between Y, which is the actual value, and the CEF evaluated at X, which means mx. So the notation will look like this one. And we can rewrite it by put E to the other side, and it will look like this. So there are two properties of the CF arrow. When the expectation of Y is finite, then we first have the expectation of the arrow conditioning X is just 0. And even without the condition, the expectation of arrow is still X. And let's prove it. So for the first one, we can replace E using this one, which is E minus mx. And the expectation, or maybe we use the average, have a good condition, like means you can separate it to two parts. And it will not influence the value of it. Then recall that this one is just mx. And when conditioning x, the mx actually is just itself. It will not influence the average value of it, because mx is just a function of x. Or if you can understand it, it will look like mx and conditioning x. So here, if we have conditioning like 2x here, we can just ignore the second one, and it will turn to be mx. And then it goes to 0 at the end. So for the other one, we could write this one. Also, this notation is the same. We can add an expectation and a conditional x, and it will not influence the, and it will just equals the expectation of error. And then because we already know this one is 0, and it will turn out to be 0. So next, we want to claim that the CEF mx is the best estimator, which minimizes the expectation of y minus gx squared. So here gx means any predictor as a function of x. And here y still means the exact value. Yeah. And actually, it's kind of the same idea what we used during the class to find the closest point. You can eventually get this idea from the proof, I think. So first of all, let's use the mx. plus arrow to substitute y here. And then let's separate it and expand it. So we will have first the square arrow term, and we can factor out 2 here. So we use this one as the first part and this one as the second part. Then let's say here, we know that E is just the condition. The arrow term of this one is just 0, and actually we can write down this one too. And then because this one is 0 and the whole things will goes to 0, and we can just cancel it. So it will remain the 2 parts. Then it will be greater or equal to the expectation of the arrow square, unless mx is just gx. And also we can write down this one as y minus mx squared. So finally, we can conclude it by the conditional expectation as best predictor. So when the expectation of y squared is finite, then for any predictor gx, the CEF mx is the best estimator, which minimizes the distance between y and this function.